Okay, if you are watching this video, it's probably because it's a snow day and your class has not yet done the heat of combustion lab. Um, in the lab, we're going to take a candle, as you see here on the left, and we're going to use that candle to heat up a beaker of water. Um, and what we're going to do is explore the amount of heat that is contained in a candle. So let me show you this cheesy video I made, and then we'll go from there. The key here is that a candle, in this case, it has a mass of 247 grams to begin with. Once I light this candle, let's see if I can do that through the screen there. The candle starts to burn and it releases heat through the flame, right? So there's something going on. Earlier in class, we learned that if something freezes or melts, there has to be a heat release. But in this case, what we have is a chemical reaction that is happening, that is releasing the heat. And it's coming out of the chemicals themselves. So it won't be a heat of fusion or a heat of vaporization. And in this case, it's going to be what we call a heat of combustion. It's the same thing as a delta H that you would find anywhere else. Now, I don't think my scale is going to show it because it's not a very good scale. But the longer I let this thing burn, the less this will weigh. So it still weighs 247 grams. But you should know that over time, if I let this thing burn for a few minutes, that the candle is going to get shorter and shorter and shorter, which means it's going to weigh less. So the question is, how many joules of heat come out for every gram of candle that gets burned? So that we're going to call our delta H of combustion. All right, so let's take a look at this here. Um, so an intro to heat of combustion. Basically what I need to tell you is that these are the same math problems you have been doing for the past 2 weeks. There's really nothing new about them. It's just that the vocabulary is changing. So when a fuel burns, in that case I showed you a candle, but it could be any kind of fuel, the mass of the fuel is going to decrease and heat's going to come out. Basically, a chemical reaction is going on. The fuel is probably disappearing as a gas, and heat's coming out because of that process. So we call that thing a heat of combustion. And if you really want a formula for it, it's the amount of heat that gets released divided by the grams of fuel that are burned. And it has units of joules for heat and grams for mass. So a sample problem might look like this. You have a 147 gram candle, and you're going to use it to heat a pot of water that has 234 grams of water in it. The candle is lit and put under the pot of water, and the water's temperature goes from 21 to 33 degrees C. If the final mass of the candle is 146.2 grams, what is the heat of combustion for the candle? So the first thing is that we're going to make some crazy assumptions. We're going to say that all the heat that was contained in the wax of the candle, the fuel of the candle, goes into the water. It's a terrible assumption because heat's going into the air, heat's going into the pot, but let's just keep it simple and say any heat that was in the candle is going to go to the water. So the candle itself is not changing temperature. So we can't use a delta T in that side of the equation. All that's happening is the candle is burning. The wax is evaporating, catching on fire, and releasing heat. So that is an M delta H. And the water isn't doing anything fancy either. It's not boiling, it's not freezing or melting. So we use the MC delta T because the water is changing temperature on that side. So let's plug in our numbers. We didn't burn the entire candle, so it wasn't 147 grams of candle. The candle went from 147 down to 146.2. So we only burned a part of the candle. and we're looking for the delta H of that candle. For the water, we know that we have 234 grams of water. You know that the C for liquid water is 4.18, and if you don't know that, you can look it up in a table. And the temperature change is that we ended at 33 degrees and we started at 21. So we're going to subtract those and get 12. So if I simplify that a little bit, 147 minus 146.2 is 0.8 times my delta H. And if I multiply my 234, 4.18, and 12, I'm going to get 11,737 joules. So if I rearrange, do some algebra, I get 11,737 divided by 0.8, or my delta H of combustion is equal to 14,672 joules per gram. Wow, that's a mouthful. So chemists will usually shorten that and just say, hey, that's 14.7 kilojoules per gram. So you've seen this equation before, this M delta H equals MC delta T. It's the same exact equation you've been using. If something crazy like the candle were to heat up and boil the water, then you would use MC delta T at plus and MH over here. You just adjust the equations to match whatever problem there is. All right, guys.